Recently we found a mail in our inbox, a mail by Jesper, sorry for mispronouncing your name by the way, and he asked about this optical illusion and how we would create such a thing. So here is our take, or how we would do it. So basically this illusion combines two different techniques. On the one hand, halftone, which is a classic technique from newspaper printing, and on the other hand, perspective projection, which is how some of the classic special effects in movies, such as Close Encounters of the Third Kind or E.T. were pulled off. First, let's look at the halftone technique. Let's look at a grayscale image, and each of those images' pixel can have a value between 0, which is black, and 1, which is total white. And halftone works by taking a pixel's blackness value and using that to drive the scale of a given dot. So the darker a pixel, the bigger a dot on that position. And when we just color these dots black and move away from all these dots, they form a grayscale image. It's kind of a form of really ancient rasterization technique, and it's been there forever in newspaper printing. But how do we stack those dots or spheres in 3D? Well, that's where the perspective or forced perspective comes in. Let's assume we have something like this. Here is our camera looking into the scene, and in the center line here is a sphere with a given diameter, and it's a given distance away from the camera. So when we move this sphere closer to the camera, say half the original distance, the sphere appears bigger. It appears to be exactly twice its original size. So in order to make the sphere appear as big as it was originally on its original position, we would have to scale this down by a half. Now let's look at a second sphere above the optical center axis of the camera, which I denoted here with its y-coordinate. When we have this distance to the camera as well, you see the point jumps visually because it almost is out of the camera frustum here. From here where it has really much space to the top border of the camera frustum, it almost crosses it here. So the sphere appears too high in the frame, and we can also fix that by having its y-coordinate. So basically all we have to do to make a given sphere appear perspectively correct is we have to know how far it is from the camera compared to its original distance, and then multiply on the one hand the sphere's scale, the sphere's y-coordinate, and also the sphere's x-coordinate by that factor. Let's build that in Houdini. The first thing we need to create in Houdini is a grid where we store the pixel values onto. So let's drop down a grid, dive in, and let's scale down the grid size and increase the point density, say to 100 by 100. Then let's load an image onto that by dropping down an attrib from map. And what that does is it automatically reads in an image. For example, let's use one of Houdini's built-in example images by typing in mandrill.pic in here and highlighting the SOP, and we can see we have now loaded this placeholder image on here. Let's, in here, by right-clicking on it, disable the specular so we can see. We have now this image of a mandrill loaded onto our point's color value, which we can see when we head into the geometry spreadsheet here. We have now color diffuse red, green, and blue values on our points. Now let's drop down a transform and rotate this grid so it sits upright in our scene by rotating it minus 90 degrees around its x-axis, like so. Next, let's drop down an add SOP and get rid of everything except for the points by just checking delete geometry but keep the points. So we end up with this colored points here now. Next, let's take care of that halftone effect by dropping down a point wrangle and writing a bit of VEX. What I want to do first is create two input sliders for the X and Y resolution of our grid, or assuming our grid will stay square, we can make do with just one slider for either the X or the Y resolution. Let's take the X resolution and pipe it in through a slider, an integer slider that is, and let's call it resolution X. Click this button here, so we have our resolution slider here, and in our grid, let's right click on the columns here, say copy parameter, and paste as a relative reference down here in our point wrangle. So we now have those two slots linked up. Next, in order to calculate which maximum radius one of those individual dots or spheres can have, we also need to get the size of our grid. And again, assuming the grid will always be square, we just need one float here. Let's call that size X. And let's drop down a float slider and call that size X. Again, create that slider. And in here, we're going to wire in the grid size X. So again, we copy that parameter. And down here, right click on it and say paste relative reference. Now that we have that, we can calculate the maximum size of a given point. Let's create a float called scale. and this is the maximum scale one dot can have, and it's going to be size x divided by the resolution along the x-axis, and by dropping down float here, I'll make sure that this division will yield a float result and not an integer result. Now what I want to do next is calculate a brightness value from each individual point color, and then use that to scale the individual dots, and write that down into a p-scale attribute. So first let's read out the color, and then convert that into a brightness value. And I'm going to just do that by averaging it out. So I'm going to create a float, let's call that gray for grayscale value, and I'm going to calculate that brightness value by averaging all the individual components in the color vector. So I sum them together and then divide them by 3. Okay, now I have everything, so I can calculate now the p-scale. So I'm going to create a new attribute called p-scale, and it's going to be float. And my new attribute will be 1 minus the gray value in order to account for bigger points, the smaller the gray value is. So darker points get bigger. And I'm going to multiply that by the maximum scale my point can have. And as I want it to be a radius, I will multiply it by 0.5, so I don't get a diameter, but a radius, like so. So let's highlight that node, and in the GeoSpreadsheet check, yes, we have a p-scale value written on all those points. Now what I can already do is drop down a color node here, set this to black, so all my points now get a black color here, and then after that, drop down a copy to points, wire in those points here, and wire in a sphere on the other slot, and highlight that. So I can see now my halftone effect is already working here. Now how do I stack those points in 3D while maintaining the optical illusion of this being a halftone print in 2D? Well, first let's create a camera for this. Head up one level and just control click on the camera symbol here. So we create a camera now, and I want to set that to its original point, and let's say minus 2.5 along its z-axis. And I don't want much rotation, just this thing looking straight into the scene, and then dive back into our grid geometry here. In order to arrange those points perspectively correct into our scene, I need to know the distance from the points to the camera. So let's drop down another point wrangle and create some input fields so we can pipe data into this node. First we're going to need a vector for the camera position. So let's create an input field for that and call it cam position. Let's create it, and in here I want to have my currently selected camera's position, so let's head up one level, select the camera, right click on the translation here, copy the parameter, head back into our grid and onto the point wrangle, right click on the cam position input slot and go to paste relative reference. So now we have the camera position in here. So how do I decide how close a given point is towards the camera? Well, in my case, I decided to just do it randomly, and in order to be able to control that random generator a little bit, let's create an input slider for a seed value. So that's going to be a float called seed. Now let's create a slider. Call it seed as well, so I can dial in any seed value that I'd like. Next, I want to be able to dial in how strongly those individual points will be moved along their z-axis, so how far they are allowed to move towards the camera. I decided to call that amplitude, so another variable called amp, and also create a slider called amplitude. And in my case, let's set this to something like 1.3. Another variable that I'll need is the current points position. So I'm going to create a vector, let's call it pos, and that's going to be our current points position. Now the first thing I can calculate is the distance from an individual point to the camera, and I'm going to do that by creating a variable called zdist, and it's just going to be our current points position in the z-axis minus our camera's position z-axis. Now let's first calculate the z-offset, and that's been done randomly. So create a float called z-offset, and that's going to be a random number, and let's use the current point number plus the seed as a seed value for the random number generator, and let's multiply this by our amplitude, like so. Let's check if that's correct. Okay, looks good. Now when you think back to the diagram that I've shown you, we also need to calculate the offset along the x and y axis. So let's do that. by creating a variable called xy offset. And if you think about it, the closer a point is towards the camera, the smaller its offset should be. What that means is, the closer our z offset gets to the z distance, this is the distance of the camera and the original point, so the closer this offset value gets to this distance value here, the smaller the xy offset should be. Let's calculate that using just a fit node. And what we're going to do is we will fit the z offset value, which should be somewhere between 0 and our maximum z distance. And we want to map that to be either 1 if the z offset is 0, or 0 if the z offset is equal to the z distance. So if the point is basically on the camera. And this is all we need to calculate on the one hand, the new position of a given sphere, and on the other hand, the scale of that given sphere. So let's first calculate the new position. So this is the vector, so we want to use the set function to set that vector. And it's going to be our original x value times the xy offset. It's going to be our original y position times the xy offset. And it's going to be the original z position minus the z offset. Like so. Let's drag that over here so we can see. So when we go back into that Illustrator file that I shown you earlier, what we calculate with this is the closer a point moves towards the camera, the smaller this factor here gets. And what we just did is we just multiplied all the coordinates of that point by that factor. The last thing I need to do is calculate our new scale. So let's take the original p scale and multiply that with our xy offset value. Okay, let's save this, keep our fingers crossed. And what I can already do now is move my camera away from the central perspective. And I see now, I moved all those points according to their distance from the camera, and it forms this frustum. So let's highlight the copy to points here. And we can see now they have different sizes here. So let's move back onto our original camera, and I can see now my illusion is perfect. I just took care of scaling and moving my points around as they get closer to the camera. Okay, so far for this optical illusion, but we have also gotten other mails from you that were asking why we prefer to use VEX over VOPs or why we focus so much on VEX. And although I'm not a big fan of building a setup as this in VOPs, just for the sake of being able to compare both approaches, let's build the same setup in VOPs. So let's supplant these 2 point triangles here by 2 point VOPs. And on the first point VOP, I want to calculate exactly the same thing as in the first point triangle. That is the p-scale, because all of what we're doing here is just to calculate the scale of our dot. So what I'm going to rebuild in here in the point VOP will be actually this expression here. So 1.0 minus the average of our color times the scale, which is this formula here, times 0.5. So let's dive into the point VOP, and let's first calculate the average of our color with a node called average vector component, which will do exactly what my formula for the average in the point triangle did. So I have this average, and I want to complete the formula by going 1.0 minus this average. So let's drop down a constant, set that to 1, and after that drop down a subtract, and go 1.0 minus this average. Let's go up one level and have a look at the point triangle. So we just took care of this and this bit here. Now I'll have to multiply it by the scale, and the scale is the size divided by the resolution. So set into the point VOP and drop down a divide here. And we want to expose both input slots here. So middle mouse click on that, go to promote parameter, and the same for the second input slot. Let's go up one level. And on this point VOP, I now have those 2 inputs here. And by clicking on the edit parameter interface, I can give those inputs labels. Let's call the first one size X, hit apply, and the second one resolution X. And we hit apply and accept, and I'm just going to go over to the point triangle and copy those expressions over. So this is the resolution expression, goes in here, and this is the size expression, goes in here. like so, back into our point VOP. So we now divide the size by the resolution. Let's compare this to our point wrangle. So this yields this. So what we have to do now is multiply the result of this expression with the result of basically this expression and times 0.5. So into the point VOP, and we're going to drop down a multiply. And we're going to multiply this subtracted average times our division, which is the scaling factor, and we also need a constant, which is 0.5, and wire this in here. And now this output here should be bound to our point attribute called pscale. So let's do that using a bind export node. Call the parameter here pscale. It's going to be a float, and then just wire this up. So this is basically our point wrangle rebuilt in VOPs. Let's go up and rebuild the second point wrangle here. Drop down another point VOP, wire this up. And what we need to do here is, using the distance between our camera position and our point's position, calculate the offset along the x and y axis, as well as the new p-scale, and also randomly generate the z offset. So let's go into the point VOP, and the first thing I want to do is calculate the distance between a point and the camera position. And I'm going to do that by first dropping down a vector to float conversion and piping in the position here, so I can now access the x, y, and z position individually here. Next, I'm going to do the same thing, but this time I will promote the input here, promote parameter, and up one level onto this point VOP. I'm going to pipe in my camera's position in here, and again I will just copy the parameter that we already set on the point wrangle and just paste it as a relative reference in here on the point VOP. So we have the same camera position as on the point wrangle. Now let's go back into the VOP, and now I'm going to calculate the z distance by subtracting from our current point's position's z value the z value of the camera. And let's call this one z dist, just for clarity. Next, we want to randomly generate a z offset. So let's use a random generator for that, which hides under the random node. And we want a 1D float input and a 1D output. And we're going to use the current point number as an initial seed, but also we want to be able to dial in that seed. So we're going to add an add node and promote this input parameter here. Go to promote parameter and go up one level. And on our point VOP, we have this input number 2, which is the seed now. So let's edit the parameter interface. And the vector should be the camera position. And input number 2 should be our seed. Like so. Okay, back into the point VOP. And in order to generate the z offset, all we do is we multiply this random value by the amplitude value. So drop down a multiply node here, wire in the random output in here, and promote the second parameter as well. Go up one level. And again, in that parameter interface, let's call this one amp for amplitude. Set this to 1.2 and dive back into the point VOP. Now, using our z offset and the z distance, let's calculate the actual x and y offset by using a fit node, just as we did in the point wrangle. And we would like to fit the z offset that's coming in here. By the way, let's call this one z offset, and let's call this one xy offset. Okay, we want to use the z offset, which should go from 0 to our z distance. This is the maximum it should go to, so let's wire this in the source max, and we want to remap this to be between 1 and 0, like so. Now we finally can use that xy offset to calculate the new positions with a couple of multiply nodes. So first we're going to calculate the new x position by multiplying the old x position with the xy offset. Just copy this node over and wire in the y position in here. So we calculate the new y position, and also we'd like to calculate the new z position, which is done with a subtraction. So from the original z position, which is coming in here, we would like to subtract the z offset here, like so. Now I need to convert those 3 individual values back to one vector value. It's done with a float to vector, x, y, and z value, and the resulting vector will be the new position, so let's write that out. And the only thing that's missing now is taking care of the p-scale. So let's import the old or current p-scale by using a bind node and import the p-scale. So we import this and let's multiply this with our x and y offset, like so. So it's xy offset times p-scale now. And we want to export this again to the p-scale value, and we're going to use a bind export node for that. And we're going to write out our newly created p-scale value by wiring this up in here. And that should be it. And although this is not really bad, one reason why I prefer VEX over VOPs is that to me it seems more straightforward just going through a code line by line and going through which variable does which thing. While I might be able to read out the data flow in a diagram like this, it makes it harder than it should be, I think. But nevertheless, this is how you would build the thing in VOPs. So let's check if that worked. Okay, nothing bad happened so far. Let's wire this up in here and highlight our copy. That's looking good. Let's select our camera, and yeah, same result as with the point wrangle. So these are two approaches how you can build this optical illusion using either VEX or VOPs. As always, I hope you had fun with this. If you create any artwork using that technique, please let us know. We're always intrigued to see what you guys create. And it's cheers and goodbye.